Hi, and welcome back to Codex. Our speaker today is Stephen Flammia from Virginia Tech. Dr. Flammia is an expert in quantum information theory and quantum computing. Today, he'll tell us about some exciting breakthroughs on Zauner's conjecture. Take it away, Steve.
Thanks, Emily. It's great to be speaking again at Codex. My co-authors and I have all spoken about aspects of this. We've been working on this paper. So this paper you can see here with my co-authors, Marcus Appleby and Gene Kopp. It's like about 180 pages long, and we've been working on it with some breaks for about 5 years. So some of the things that I'm going to talk about today have appeared at prior uh, seminars at Codex, but I hope that the overlap between those talks will be at most pairwise constant. So I will, so I'll tell you about our work on Zauner's conjecture. I'm very excited about it. So Zauner's conjecture is equivalent to, I'll start instead. I see some quantum information or quantum information adjacent people on this call. So I'll just say a little bit about this with a slightly different language. Sorry, excuse me, which is in terms of these objects called SIC-POVMs, which stands for symmetric informationally complete POVMs. So a SIC, it's pronounced seek as opposed to sick, is a set of d squared complex equiangular lines. Okay, so you can equivalently, you can consider this as d squared rank 1 Hermitian projectors such that their pairwise Hilbert-Schmidt inner product is either 1 if j equals k, because they're rank 1 projectors, or 1 over d plus 1 if j is different from k. So an example of this, if I use the representation of complex projective space and I look at sort of two-dimensional projectors, rank 1 projectors in a two-dimensional space, I can represent that. Quantum information people know this as the Bloch sphere. This is just a standard representation of CP1. Then the vertices of these projectors, represented as vectors in this space, are just the points of a regular tetrahedron. So this is an example of one of these things. So why is this condition interesting? D squared rank 1 projectors with pairwise constant overlap. There's a huge number of interesting properties that these things have. So for one thing, it can be proven that this is the maximal number of complex equiangular lines in d dimensions. They form a minimal complex projective 2 design. That is to say, if I average any degree 2 polynomial over the uniform measure on the unit sphere in CD, then this is equivalent to a discrete average over these individual points that I get from this seek. They saturate a lot of other extremal criteria. So I'll just run through a list of these. It's okay if you don't understand what all these things mean. It's just to sort of show you that these things sort of come up a lot as extremal or optimal objects. So they're a maximal equiangular tight frame. Some of these are kind of obviously equivalent if you're maybe not obviously, but if you know the field, then some of these things are obvious equivalences. But they're maximal equiangular tight frames. They saturate the Welch bound for k equals 2. They provide an optimal norm constant relating the L2 norm to the Gowers uniformity norm, U3, over the group Z mod D. They're an optimal for some specific and natural loss function. They're optimal measurements for quantum state tomography. They offer an improved rate for certain quantum key distribution schemes. They offer increased efficiency for something called shadow estimation, which is a really cool technique for extracting. It's similar to a classical method called adaptive data analysis, but for quantum systems. But then, the the big question is, do they exist? So I showed you one example in d equals 2. So the real question is, do they exist in every dimension, or at least even just an infinite family of dimensions? And in 99, Gerhard Zauner conjectured, he actually conjectured something much stronger than this, but the simplest and weakest form, which is still open, is he just simply conjectured that these SICs exist in every dimension D. So what's the state of play? So a lot of people, starting with Zauner, and notably people like Scott, Grossel, Appleby, Kopp, and others, have constructed examples of these things in low dimensions. So we now have exact, I think Marcus Grossel is potentially even on this call and has done a large number of these. He's constructed examples in a huge number of dimensions that are exact. And you might think, well, okay, what's the problem? Isn't there some inductive proof? Once you have 53 examples in dimensions, 2 through 53, what's stopping you from just guessing the pattern at that point? We'll see why it's not so easy. So people have spent a lot of effort trying to construct examples of these things to actually understand the patterns. And in addition to exact examples, there are numerical solutions that give us confidence that these things exist in dimensions, every dimension up to dimension 193, and several higher dimensions as well. I think Grossel emailed me that I think he can do this in 194 now as well, and maybe also 196. But okay. The point is, there's a lot of these dimensions where we have either exact or numerical examples. However, there are only finitely many dimensions with known SICs. There's no infinite family that is known. There's a 2,025 euro prize as of this date for finding an infinite family. And that's still open because we don't do that. Okay, so just a little bit more about these objects. With exactly one exception, every known SIC is covariant with respect to the Weil-Heisenberg group, which I'll denote WH of D. This is sometimes called the QDIT Pali group. It's just the d-dimensional clock and shift matrices. So I introduce a d-through of unity, and I'll also introduce this constant xi, which is minus the square root of omega, okay? And then I can generate this group by, so this central element here, and then shifts and phases, x and z. And so here's how they act on the standard basis. I'm using Dirac notation. So the index arithmetic here is modulo d. Okay, this is in a d-dimensional. These things are a basis for CD. Okay. And a set of coset representatives for this group modulo the center. So what does this group look like modulo its center? Modulo its center, it's just the abelian group ZD cross ZD. And a set of coset representatives that I can use are these. So these are like shifts by P1 and shifts in sort of phase by P2. And then it's convenient to have this particular polarization, to use a big word, in front because it helps the algebra work out a little bit nicer. Physicists call these things displacement operators. I think if you come from electrical engineering or something, there might be slightly different names for these things, but these are familiar from several different contexts. So when I say that a SIC is covariant, what I mean is that I can find a single rank 1 fiducial vector, a fiducial projector, which is some specific rank 1 object, and I can generate all of the other objects in the SIC as the orbit under the conjugation action by these displacement operators. So I just do all of the different translations by shift and by phase, and the orbit, the group orbit under this conjugation action generates the SIC, acting on this initial one, which is the fiducial. So this problem has a natural unitary invariance, right? Obviously, I can rotate the entire space CD by a unitary. It doesn't change any of these properties. Once I enforce this Weil-Heisenberg symmetry, then the notion of equivalence reduces to this notion of the extended Clifford group. I'm not going to define this group. It's like a normalizer together with some anti-unitary conjugation operations in the standard basis. But this becomes a natural notion of equivalence class that you get on these SICs once you enforce this Weil-Heisenberg group covariance. Now, because this is the only case that we study here, it's very interesting to ask if there are besides this example due to Hogar, it's very interesting to ask if there are non-Weil-Heisenberg covariant SICs, but I don't have anything to say about that today. So I will restrict my attention. All of my statements will be qualified by Weil-Heisenberg symmetry and further qualified by D is greater than 3, and that's to rule out some pathologies that happen in dimensions 2 and 3. Yeah, I'll have a little bit more to say about equivalence later, but basically everything that I say I won't say explicitly that it's restricted to these two cases here. Okay. Okay, so in the title of my talk, I use something that maybe many of you are not very familiar with, which is something called the Stark conjectures. And I'm not an expert on the Stark conjectures. I'm fortunate that my co-author, Gene, is. So I can give a lay person or a lay mathematician's, a non-number theorist's overview of the Stark conjectures and what they're trying to say and why they're interesting. If you're going to ask me deep questions about it, then I hope Gene is on the call and can chime in. So basically, our main result is a construction of SICs, but conditional on two conjectures, one of which is a specific Stark conjecture. And the other one, which I'll talk a little bit more about, is what we call the twisted convolution conjecture. So the statement is, if this specific Stark conjecture is true, and this twisted convolution conjecture is true, then Zauner's conjecture is true, and moreover, via an explicit construction. So this is a constructive proof, conditional constructive proof of Zauner's conjecture. However, construction is a little bit weird, as we'll see. You tend to think of constructions as being the same as algorithms. And in a formal sense, that might be true, but we'll see that the algorithm is a lot more involved than you might hope in order to actually execute this construction. So I'll explain why that's the case and why it's kind of fascinating and also frustrating. Okay, we need a little bit more terminology in order to explain these results. So once I've enforced this Weil-Heisenberg symmetry, I can use the pairwise equiangular property to write out the fiducial vector. This is some presumed fiducial projector, excuse me, some presumed fiducial projector pi. I can write it out in terms of these displacement operators. So the displacement operators form a basis for the space of matrices. And because of the equiangular condition, I can always, so it's a projector with rank 1, so its trace is 1. It's Hermitian. And because it's equiangular, it's straightforward to prove a couple facts. One, these expansion coefficients, after I pull out some normalizing factor, are complex unit phases. Okay, so theta here is a real number. So these nu p are just complex phases. They live on the unit circle, and they have a symmetry, which is just that nu p times nu minus p is 1. That's just the Hermiticity symmetry that you get. So it's very easy to prove that from the definition of a SIC. This is equivalent. Saying something is a Weil-Heisenberg covariant SIC is equivalent to this expansion with these conditions. Okay? So there was a long series of works studying these exact solutions, trying to find some patterns by many authors. And I can't list all of them, but here's a important subset. And one of the insights that was obtained from this long series of work was that these things are somehow very special objects. And it culminated in showing that in every case that people had studied, these objects knew were Galois conjugates of Stark units over the rational field adjoined with some specific square root. Okay, so I'll unpack all this if you're not a number theorist. So in d dimensions, this number delta has some specific form, and I append the square root of delta to the rational numbers. That gives me like a two-dimensional vector space over the rationals. And recall how conjugation works in such a vector space. So conjugation is like a q-linear operation on that vector space, a lot like how complex conjugation is an r-linear operation on the vector space. If I think of the complex numbers as like r adjoin I, and then complex conjugation just flips the sign of I. Galois conjugation is almost exactly like that, but it's a q-linear operation instead of an r-linear operation. That's important. So for example, if I have the vector space q adjoin root 2, or the field q adjoin root 2, then, I mean, it's a field automorphism. It's stronger than q linear. Then I just flip the sign of root 2, okay? And it fixes the rational numbers. So That's how Galois automorphisms work. If you understand complex conjugation, you've got a good understanding of Galois conjugation. Okay, but they're Galois conjugates of these things, Stark units. What the heck is a Stark unit, and why are they special? So I'll only give a basic understanding of this. And basically, Stark units, and it's closely related to an open Hilbert problem, Hilbert's 12th problem. Stark's conjectures and the associated units assert that certain special points of transcendental functions are actually algebraic. Okay? So what it's trying to do, I mean, you can sort of guess by just looking at these two, uh, transcendental functions on one hand, algebraic on the other. What it's trying to do is build bridges between analysis and arithmetic. Okay? And it uses things that I'm not going to go into detail on, but certain types of zeta functions or L functions, which are things I'm sure many of you have heard of. Maybe some of you are experts on these. It's trying to relate logarithms of absolute values of certain units in algebraic number fields. That's on the arithmetic side, to values of derivatives of certain specific zeta functions, these partial zeta functions, or equivalently L functions at certain specific values. So S is kind of like this S parameter you have in the Riemann zeta function, but for other more general zeta functions. So it's building bridges between these two worlds and allowing us to take analytic statements, connect them to arithmetic statements, and vice versa. So the Stark conjectures is a whole bunch of conjectures, actually, but we only need one special case for most of our results. We need the so-called order 1 abelian Stark conjecture for real quadratic fields. So this goes back to the fact that on this slide, we have this Q adjoin square root of delta. That's just a real quadratic number field because this thing is just a quadratic irrationality. Okay. So it would probably help to see some examples of this, but I'm not going to go into, I'll give maybe some examples of the phenomenon rather than specific Stark conjectures. So one of them, one of the problems that this gives insight into, or that this was, these conjectures were aimed at providing insight into, is what are I forgot to define what an abelian extension is. So if I start with a field, and I add some root of some polynomial, I can ask about the symmetries of that. That's the Galois group. And I can ask whether or not those symmetries are abelian. Okay, so that's extending a field and then asking if those extensions are abelian, if the symmetries are abelian. So the abelian extensions of the rational numbers are all generated by special points on the unit circle, namely points where this exponential map, e to the 2 pi I z, is evaluated at a rational number. So here here's the unit circle, and these red points are all the rational numbers that you get with denominator 7 or less. And I've plotted them here. Those red points are all algebraic points, even though a generic point on this circle is transcendental. And it's sort of stronger than that. Not only is it algebraic, but these symmetries as a number field over the rationals, those symmetries are themselves abelian. So they're not somehow general. This is closely related to the notion of solvability as well, right? So there's another example, and it comes from the study of elliptic curves that have something called complex multiplication. So elliptic curves are functions defined by two periods. They're doubly periodic functions. One of them can be chosen to be real, and the other one has a positive imaginary part. And so it's a function which you can think of as having these two periods. So it's defined in some fundamental domain like this. And if I subdivide that domain by some denominator, in this picture, that denominator is 4, then these points here are called torsion points of this elliptic curve. So sort of like how I divided this circle with some denominator, I chose a rational number, it had some denominator. These torsion points are analogous to this, right? I've subdivided the two different lattice directions by some denominator, in this case 4. If I evaluate the elliptic curve at these torsion points, then those special values are algebraic. They satisfy polynomial equations on an otherwise transcendental function, right? So this is kind of surprising. Now, remarkably, these are basically the only proven cases of this. We need the simplest unproven case, which is abelian extensions of a real quadratic field as opposed to this imaginary case. Okay, there are maybe some other ones. I say essentially is kind of a weasel word, but this is essentially the state of the art is these two examples, and we need the Stark conjecture for the real quadratic case, which is still open. Okay, so I hope that gives you some flavor for the Stark conjectures, like the types of questions that they're meant to address, connecting arithmetic and analysis, why they're important. So I'm going to introduce something, a tool that we use to study these, which we call ghosts. And to motivate that, I want to just recap this definition of this SIC fiducial vector. So remember, we saw that I can always expand this thing in the displacement operator basis. And it's these special things that have special, it's these expansion coefficients, which we called the overlap phases, that have special algebraic properties. So I have expansion coefficients that are complex unit phases, and I get this equation from hermiticity. So now, having studied the solutions and seen that they're conjugates of these Stark units, it turns out all of these Stark units for real quadratic number fields, they're always real numbers. And here's an example of what they look like. This is what you get if you do the math for d equals 4, and you solve the SIC problem for d equals 4, and you write out what these numbers are, and then you write out what their Stark conjugate numbers are, and you put them on the number line in blue, and this is what they look like. The fact that these two polynomials are themselves conjugate over q adjoin root 5, so delta for here, I should have wrote delta is d minus 3 is 1 times d plus 1 is 5 here. So we expect to see a root 5, and we do. A root 5 comes out. So I see these red points are the roots of this polynomial, and these blue points are the roots of this other polynomial, which you can see is the conjugate of the top polynomial. So p and q are conjugates. And if I multiply p and q, I get a rational polynomial. In fact, a polynomial with integer coefficients. In fact, even stronger than that, I get a monic polynomial, one with integer coefficients, and the leading coefficient is 1. Okay. So these numbers, these red numbers and these blue numbers are dual in this Galois conjugate sense. And so what we're proposing is to try to learn something about the red ones by studying these blue ones. Okay, so we're going to try to define ghosts as being kind of the blue analogs of these red SICs. Okay, so what's the definition? So we're going to relax the hermiticity condition, but we're going to keep the algebraic constraint that the overlap phases obey. Okay, because that condition will be preserved by Galois conjugation, so we want to keep that. But hermiticity will not be preserved. So I drop the hermiticity constraint. I mean, you could be a little more formal and say not necessarily Hermitian, but it turns out it has to be specifically non-Hermitian. So I'll just say a non-Hermitian projector. So that by that I just mean like a rank 1 matrix, maybe up to a sign. And I insist, because these Stark units are always real, I insist that these expansion coefficients are real. Right? So the intuition here is, right, sigma of UP should equal nu P. Okay? Whoops. Oh, yeah. Should have done it like that. Yeah. Right? So this is some Galois automorphism. And if I just apply that, I should get back over to SIC world starting from ghost world. Okay? So what we would like to do is define these ghosts, study them, see if we can prove that they exist. And then if they do, hopefully we can conjugate them and land safely in SIC world. Okay? That's the intuition. Okay. So It turns out that the ghosts are labeled by something we call admissible pairs. More generally, in our paper, we call them admissible tuples. We'll talk about that. And this labeling scheme, incidentally, it explains a lot of the richness of SIC, what we call phenomenology, which is basically the empirically observed properties of all of these exact solutions that people had constructed over the last 25 years. The number of orbits, the number of like structures of various symmetry groups that these things have. It was all sort of very mysterious, and it looked like a bunch of one-off weird things. And more or less, admissible pairs and how these things are defined really explains a large fraction of it. Basically, we've been able to prove a lot of this stuff. Things that we haven't proven, we feel like we just haven't bothered to prove yet, rather than they're unprovable. So I think many of these things are given conditional proofs by this formalism. So what is an admissible pair? Consider a dimension D and let Q be a binary quadratic form. Okay, so a quadratic form, I just think of a quadratic form in two variables, which I can either write out explicitly as like ax squared plus bxy plus cy squared, or I can use this shorthand notation, ABC. So take a binary quadratic form. We say that the pair dq is admissible if this magic number delta divided by the discriminant of q, so the discriminant is just b squared minus 4ac, if that's if that ratio is a perfect square, okay? So in that case, we take that integer, like we take the square root of that integer, and we call that the conductor of the pair. And we also let Q adjoin root delta. We call that the associated field. Okay? So it really is just an integer D and a quadratic form that has some special property that relates the discriminant of that form to this magic number delta. Okay? That's all an admissible pair is. But there are consequences with equivalence of pairs and equivalences of ghosts, okay? So we had talked about unitary or anti-unitary equivalence of SICs and how it was related, once you have Weyl-Heisenberg symmetry, to this extended Clifford group. So we can talk about equivalence between these pairs because there are equivalence relations between quadratic forms. So unitary and anti-unitary equivalence of ghosts is very closely related to equivalence of quadratic forms, but now the equivalence relation is similarity of forms. So for a given dimension D, it turns out we will have a many-to-one map from admissible pairs to ghosts in dimension D. So two ghosts are unitarily or anti-unitarily equivalent if and only if the corresponding forms in their pair are equivalent under some similarity transform. So I take some GL2Z matrix and I do L transpose QL to get a new form. And they're related by, so maybe I don't want to scroll back, but remember we had these polynomials. It was like 1 minus root 5 x squared plus 1, or I don't know, plus or minus, depending if it was a SIC or a ghost. There's a Galois conjugation that flips the sign of root 5, but there's also Galois conjugations that permute the roots of this polynomial as well. Okay, so there's another Galois conjugation which is floating around. They just permute those roots on the unit circle, or they permute the roots on the real line, the blue roots. And this sign switching thing switches red and blue, but of course there are things that preserve red and preserve blue. So those Galois conjugations that preserve red and preserve blue, two ghosts are related by an anti-unitary transformation, and some Galois conjugation on these roots, fixing root delta, if and only if the corresponding forms have the same discriminant. Okay? So that gives us some equivalence relations on these pairs, which then relate quite closely to equivalence relations on ghosts. So the set of ghosts corresponding to all forms of a given discriminant we call a Galois multiplet. Okay? So in general, there's more than one of these because there will be non-trivial automorphisms that I can do on this polynomial. And so that will give me, there will be non-trivial symmetries of those roots. And so that will generate more than one of these things. Okay, I think we should do an example. So in the special case d equals 35, the magic number delta is d minus 3 times d plus 1 is 1,152. And the different possible conductors, right? So now I take this thing and I can write it as a square-free part or a fundamental discriminant times a square. And the valid squares that I can put in front are the allowed conductors, 1, 2, 3, 4, 6, and 12. And each one of these is going to give me a different set of quadratic forms that I can use to try to label ghosts. And some of these are going to have certain degeneracies because they will have some non-trivial Galois structure in their roots. Okay. So the Galois multuplets corresponding to 1, 2, 3, and 4, they don't have any of this substructure. So their roots are kind of frozen. You can't permute them in any interesting way. But for 6 and for 12, actually, you get some interesting structure. In fact, there are two ways to permute the one for f equals 6, and there's 4 different things in the multuplet, 4 different ghosts in the multuplet for 12. So this is a diagram from an old paper that I co-authored with several people. And the point of this is to say, like, previously we had no idea. We just gave these things labels like A, B, C. Like, we didn't know what to call these things. And we now know that these things are labeled by class representatives of quadratic forms under similarity transform. Okay, so these labels aren't exactly canonical, but they're kind of almost canonical. You can reduce them to like a finite set of things that are canonical. So they're kind of the right labels that we should have been using. So this is what I mean when I say we can explain phenomenology. People would have these inscrutable diagrams and you have no idea what they mean. And now we like actually understand what the labels are that belong to these types of diagrams here.
Steve, can I ask you a quick question?
Absolutely.
When you say we know, do you mean you know, or do you mean you have a conditional proof?
These things are, yeah, so everything that I'm saying is conditioned on at least this Stark conjecture, and most of the things that I'll say are conditioned also on this twisted convolution conjecture. Occasionally, I will need some refinements of Stark as well. So they are known but conditional on maybe something slightly stronger than Stark. This one, I think I do actually need something a little bit stronger than Stark for it to be an exact bijection here to here. I'll return to that point. I need something slightly stronger for it, but I guess in this case we do know because it's a finite specific example. But in general, to say that it's bijective isn't quite known without something slightly stronger than Stark. But I think, yeah, okay. Yeah. Oh, everything. If it's not clear, assume that it's conditional on both Stark and twisted convolution, or something slightly stronger than Stark. Okay. So we can go from admissible pairs to actually constructing ghosts by building something that we call the Shintani-Fadeev modular cocycle. Okay. Oh, and I forgot to cite Gene's paper. So Gene came up with a really nice formula for this thing, this object, in terms of ratios of what's called the Q-Pochhammer symbol, okay, which is this infinite product right here. Technically, the following definition that I've listed here in terms of these ratios, it only holds if this argument tau is in the upper half plane. And we actually need it on the real axis. So we have to analytically continue it down to the real axis. It gets complicated to do that, so I'm not going to do those details. But I did want to just show that this thing does have some reasonably explicit formula that you can write down, at least in the upper half plane. You do have to do a lot of work to get it down to the real axis, though.
Hey,
And why
Steve.
the word modular, one sec, why the word modular, it's because it has certain modular symmetries related to SL2, as well as a kind of congruence condition, modulo D, in terms of some matrix A, which I'll give some insight about in a second. Yeah, question.
Is it obvious that infinite product converges?
if the imaginary part of tau is positive, then yes, because z is fixed. And then if the imaginary part here is positive, then this is decaying. And
Oh, I
then,
is
then, then it
minus
is.
1.
But then it's not clear that there's going to be some nice or useful analytic continuation. Like certainly the formula fails when you go to the real axis.
Great, thank you.
Yeah. Okay. Right. So yeah, so as long as I have some sort of modular condition on A and some congruence condition on A, and P is like an integral vector, then this is, and tau is in the upper half plane, then this definition works. Here, when I say A dot tau, I mean like the linear fractional action. Okay. So what's our construction? So we take this continuation of this formula to the real axis. We take a root of Q. What do I mean by that? I mean like the root of the quadratic form means like the root of the associated quadratic equation. So like negative b, let's say plus the discriminant will be delta over 2a. So rho would be like the positive one of these. Okay. So rho is just a root of Q. A is either of the two generators of the following cyclic group. So this is like a stabilizer group under a similarity transform. So these m's, they all stabilize the quadratic form, and they also obey the same congruence that are required on A. Okay, so A is one of the two generators of this group. Okay. Then the ghost overlaps are given by the absolute value of this Shin function times some sign, like an SIGN sign, which I'm not going to write out explicitly, but you can write it out explicitly and easily compute it if you know the admissible pair and you know this Shin value. So then these are the things, remember, these are like the blue things, these Stark units that live on the real line that we were after. So this is as close to an explicit form as I can give you in a 1-hour lecture for these things. I can do a little bit better than that though. And this isn't in the paper. So this is like a special codex announcement. Yeah, so there's a special case, which we don't really go into any detail about this special case in the paper, but I'm presenting it for codex. For every d greater than 3, I can take the following quadratic form, 1 minus d, 1. Then dq is an admissible pair. And we call this thing the principal maximal ghost because it's associated with the principal quadratic form, or and it's got the maximal conductor. Okay. And in some ways, these are the simplest ghosts. So I will present to you today a fully explicit formula, except for the plus or minus signs, but you can look those up in the paper. So what's the formula for the principal maximal ghost? And this is uniform in every D. So this thing always exists for every D. So if you could prove our conjectures for this specific one, you would completely resolve Zauner. Okay. So I'm going to pick two integers, P0 and P1, from the sort of standard, like conceptually, these are integers mod D, but I'm going to pick them to be concrete integers between 0 and D minus 1. And then I'm going to let P2 be the element inside this set that when I add it to P0, when I subtract P0 and P1, I get 0, okay? So in particular, like P0 plus P1 plus P2 is 0 mod D, and all three of these are taken from this set, okay? So these are like sort of 3 points on a line, if you will, mod D through the origin. So now if delta is our friend delta, then this is the root that we get for the quadratic form, okay? Now I'm going to define one more thing. I'm going to define this parameter w sub k where the index is cyclic modulo 3. Okay, so P3 wraps back around to P0 here. Okay, so this is a quadratic irrational because rho is a quadratic irrational. Okay, so like WK, this guy is an element of this number field right here. Now, this actually is this famous Zauner symmetry. Those of you who know a little bit about this problem, this is this order 3 symmetry that Zauner also conjectured. It's manifest right here. And this is the formula. Yeah, it's a little messier than you were expecting, but if it was less messy, we might have been able to prove something. So this is the formula. If anybody proves Zauner's conjecture from this, like, I'll be very impressed. It's not completely explicit because you still have to do this integral. And again, I'm omitting, it's not fully explicit. You can work out what this sign is from our paper. But plugging in these values into that formula that I wrote for upsilon, this ghost projector, gives a conjectural ghost fiducial projector for every d, uniformly for every d. Okay, so this is like a mostly completely explicit thing. So I haven't told you. Yeah, go ahead.
I know how to verify whether overlaps give me a SIC if they're non-ghost. Is there a way to verify analytically?
Great question. Great question.
Yeah.
No, I mean, no, not really. But let me say a little bit more. Let me say a little bit more. I think I might be addressing your question on this slide, actually. So we would like to verify that this thing is a ghost, and therefore, assuming Stark conjectures, it will actually be a SIC. We can't quite do that. We can verify that it's equiangular. The analog, like we can verify that it's sort of pairwise equiangular, but we can't actually verify that upsilon squared equals upsilon, that is, that it's a projector. So we have to assume it as a conjecture, basically. And we postulate that these U sub p's, these Stark units, satisfy this thing we call the twisted convolution identity. So the twisted convolution conjecture says this identity is true. And this is equivalent to, we have a very different formulation in the paper for various reasons. But this basically boils down to the statement that you take that formula for upsilon, you square it, set it equal to itself, and sort of, follow your nose, and you'll derive this equation. Okay. So this twisted convolution lets us go the last mile. So we have equiangularity, but we don't have that it's a projector or that it's an idempotent. Okay. So what have we shown? So I said, Stark is this last step where we take these ghosts that we've constructed, which, assuming twisted convolution, are idempotent, so they're projectors. We want to take this and convert it into a SIC, so we need this Stark conjecture. We need to conjugate it. We need this Galois conjugation. Okay, so because of the Stark conjecture, these things are algebraic objects. Great. So all we need to do, we know exactly what we need. We need a Galois conjugation that flips the sign as square root of delta. So all we have to do, we know from Stark that these things, oh, there's a typo. There should be over d divided by d here. We know that these things live in some abelian extension of this number field. So we can just find this conjugation and apply it here, and we get this, and then we're done. Easy. But it's really not at all this easy, because think back to that formula that I showed you. It was like exponential of some integral. That's like presenting the answer as a transcendental function. In order to apply this Galois automorphism, we need to know how to represent upsilon inside a number field where sigma acts. This is extremely important, which is why I boxed it. To give you a feel for why this is the case, and if you've seen me give this slide before, you have to keep quiet. I don't want any cheaters. By analogy, suppose I gave you the following function. Okay, so it looks very similar in spirit to the thing that I showed before, right? An exponential and then an integral. Here it's like a definite integral parameterized by t, right? And I tell you, oh yeah, take this thing, a of t, and evaluate it at a of 1, and then apply the Galois conjugation that maps root 2 to minus root 2. Go. You're like, what are you even talking about? Like, it's not at all even obvious that this thing isn't just a transcendental number. And I say, okay, I promise you it's in Q adjoin root 2. I just promise you. It sort of still doesn't help you because you don't have any way to represent it over over a basis for this as a vector space, right? Like this, you would need to express this in terms of linear combinations of rationals and root 2 and maybe some higher order algebraic things. Otherwise, there's no way you know how this thing acts. So a strategy that you might pursue is, well, okay, if you've promised me that it's algebraic, what I'll do is I'll sort of write out its decimal expansion. I'll try like a guess and check. Okay, so you write it out and you're like, okay, a of 1 is, oh yeah, I meant to sort of challenge the audience to try to guess what the answer is, but I don't want to do that since this slide is on a different YouTube talk, and so somebody's gonna pretend like they just divined the answer and cheat. But yeah, you write it out and you're like, okay, this number, whatever it is, a of 1, is 2.4142135, etc. Okay, that looks a lot like 1 plus root 2. So I'm going to guess that's the answer, and then maybe I can check that that's the answer by some other independent means. And then the conjugation would just be 1 minus root 2. Okay. So you can do that, but it's not at all as easy as you might think, because this Galois conjugation operation on real numbers, that is, when I evaluate this thing to some precision, okay, is violently discontinuous. Okay, this is a plot of fractions whose denominator is at most 20. So rationals a and b with denominators at most 20. And I'm just looking at the plot of take those those numbers on the real line and look at their image under the Galois conjugation. So this is not just like a little bit discontinuous. This is violently discontinuous. So in particular, if you're like, oh, I think it's this number and I'll evaluate it to this many digits of precision, but it's actually this number, you could go from here to like up here. You could just be radically off, okay? So the point of this diagram is to show you that you may need insanely high precision in order to guess correctly what the answer is. And that precision actually gets worse if the number isn't in a degree 2 number field, but is actually it obeys a slightly higher degree minimal polynomial. I see I'm running short on time. So in principle, we can do this sort of guess and check procedure using lattice basis reduction. You like round it into a lattice and you like clear a bunch of denominators and you kind of round it into a lattice generated by this vector space like Q adjoin a few different roots of some polynomials. If you do this naively, it's extremely expensive. So what we've done is develop something that we call necromancy that still uses this notion of lattice basis reduction, which is quite numerically expensive in general, but we can get away with much smaller lattices. And we've actually implemented this. So in d equals 100, we implemented this y 100 because it sounded like a big number and it was bigger than people hadn't found all of the SICs in dimension 100. So we actually did this. And it's insane that we do this numerically, despite how violent this discontinuity is. If these conjectures weren't true, it's completely insane that we were able to do this and find 3 brand new SICs in dimension 100. So I consider this extremely strong evidence for Zauner's conjecture at this point. So just briefly, an overview of how this algorithm works. It's pretty complicated. It would be great if there were simplifications to this. And Marcus Grossel has already come up with some improvements to this, actually, I should add. You compute a very sort of low precision ghost, you evaluate that formula, and then you can use Newton's method to improve the precision. That's much better than trying to just directly evaluate that formula to high precision. Then we compute certain invariants that we call ghost invariants. And what we do is we compute these things by symmetrizing over an action of a Galois group, which pushes those numbers down into smaller degree number fields, right? Just like when we multiplied those two polynomials P and Q, and they went from being quadratic irrational coefficients to rational coefficients, we can push numbers down into lower degree number fields where the lattice, like fitting them into the lattice is like an easier thing. Then we use the Lovash-Lenstra, or is it Lenstra, LLL algorithm, 2 Lenstras, 2 Lovashes, something like this. I'm sorry to them. I hope they're not watching this. They round the ghost invariants into certain low degree number fields. Once they're in an exact representation, we can take a conjugation and we get the corresponding SIC invariants. Because this procedure had been symmetrized in an attempt to get things down to a low degree for us where we can actually do the procedure, it introduces some ambiguities because of all the symmetries that we've now foisted onto this problem. So at the end, there's an ambiguity by some Galois group element. And so what we do is we've reconstructed a bunch of these ghost overlaps on some orbit of this Galois group, but an overall shift by the Galois group is an ambiguity. And we then take those orbits, which means we know like a partial sum of some subset of things up to some shift of these new p's dp, and pi is equal to like the identity plus some constant times this. Sorry, this is some subset, not the full set. So yeah, sorry. We know a subset of these things. Whoops. So we do like a matrix completion task, in fact, which was really amazing that it kind of went full circle to an old problem that I worked on. So we can actually complete this matrix just by knowing a subset of these things because the net result is a rank 1 matrix. So theoretically, we only need to know a little bit more than order D of these overlaps. And so this procedure generates that. Okay, that's all I want to say about necromancy. I'm going to skip this slide. There's a more efficient procedure that we can use to get directly at the vector that uses a calculation of fewer overlaps. And also it gives us something that's kind of manifestly rank 1. If you want to do this for yourself, you can. Go to GitHub, go to my GitHub page, Zauner.jl. It's open source. If you fail to find a SIC using this package, it's probably owing to the fact that we're using heuristics to reconstruct these things. It's unlikely that it's because Zauner's conjecture is false. So pull requests are open if you find ways to improve these algorithms. I'm cautiously optimistic that we will get fast practical algorithms someday to compute these things with conditional guarantees on performance, maybe conditional on Stark. Going back to something I said earlier, if we we have this classification of ghosts and SICs. It seems that these admissible pairs up to admissible pair equivalents are exactly the set of all SICs. We can't quite prove that, so we have to conjecture that these things, so we can prove that these things always give SICs conditionally, but we can't prove that they're always inequivalent. So if we could prove that, it would mean that these things exactly classify known SICs. There may be other SICs out there, or in particular ones that aren't Weil-Heisenberg covariant, but that's still open. But it seems that we've captured all the SICs. I'll skip this slide. We can do things using this algebra without having to do this complicated necromancy procedure. We can say lots of things like how many SICs are there, and you can plot this. And it turns out it turns out that the number of these things is actually like growing asymptotically like D. That's provable. This is a slide similar to one I showed earlier. We can compute a whole bunch of algebraic properties of these things in advance without even constructing the fiducial vectors. And so then if you go and generate one of these fiducial vectors, you can verify these predictions. So it's pretty cool. The very, very last thing that I'll say, and then I'll stop. We can generalize this to rank R projectors instead of rank 1 projectors. These are like maximal equichordal fusion frames, or MEFs. They're like packings of R-dimensional subspaces instead of 1-dimensional subspaces. And so we have an analogous theory of admissible tuples, where R is one of the parameters. And this depends on some refinements of Stark. And the last thing, I said that was the last thing I would say. One of the reasons these things are interesting is because they actually generate more of these class fields. If you include these r-SICs, we're calling them, then we can show that you generate a positive density of these class fields, or the all abelian extensions of number fields, when ordered by discriminant. So at least sort of 7.4% of real quadratic fields, you can get all of their abelian extensions in the sense of cofinality. So that's it. I'll stop here with my conclusions. I put this up on a slide that I gave like 5 years ago, that in the next 5 years, I'm hopeful will prove the existence of an infinite family of SICs. I was wrong, because the clock just ran out on my original 5-year prediction. I guess I'm hopeful, not so much because I think that we'll prove Stark or twisted convolution even, but because if we don't have hope, then what do we have? So I'd like to believe that we'll find SICs, an infinite family of SICs, sometime in the next 5 years. So thank you for your attention.
All right, let's smash that reaction button.
Right.
Thanks, Steve.
Yeah, I'm also going to
for-
just show my slides, so if anybody's on YouTube, they can pause and see my references. And then I'll go back to here in case people have questions about conclusions.